All right, so today's lesson, we're going to be talking about graphs of sine and cosine. And just to be clear, this will not be on exam 1. Okay, so this content will be on exam 2, but it might be helpful to just kind of think about these ideas as you are sort of studying and preparing for exam 1. Okay. So we're going to go ahead and start with some what we know. All right, we've talked about this quite a bit, and I promise you that it is my intention to repeat things and to have you repeat things so that they sort of become a little stickier in our brains. All right, so let's start with our what we know about sine. What is one way that we can represent sine if, say, we had a right triangle? How might we want to represent sine? Perfect. We could represent it as opposite over hypotenuse, right? And I hope that's something that is pretty routine for us at this point. And if it's not too late, right? It's just something that I want to make sure that we're aware of is really important, right? Okay, so if we look at cosine and we are looking at a right triangle, we might say adjacent over hypotenuse. And if we were looking at tangent and a right triangle, we might say opposite over adjacent. Okay. Now, one thing I've noticed, I just graded quiz 5 this morning. Most folks are doing super well with the SOHCAHTOA. Some of us are still being being a little maybe. I think the diagrams are there, but maybe we're not reading the letters carefully. And we're mixing up which trig function we actually need to use, okay? And so my recommendation would be, if you feel like that is a mistake that you tend to make, which is okay, right? It's okay to make mistakes. We really just want to figure out how can we avoid those mistakes. And so we'll need different strategies. So one thing I would recommend, a lot of us are sort of drawing things and labeling the numbers, but maybe in addition to the numbers, maybe before you label the numbers, I would label like, this is the opposite side, this is the adjacent side, this is the hypotenuse. And that way, when you put your numbers in, you kind of know which ones are which already. Okay, so if that is you, where you're like, oh, I do keep mixing up my trig functions, maybe taking this extra step here of labeling the hypotenuse, opposite, and adjacent will be something that you'll find helpful, okay? And we never know until we try, so we'll just sort of leave it out there, but I hope that we try some different things, okay? But if we sort of peek below here, we notice that we have a unit circle, right? Our best friend in any trig course is knowing all the values of this unit circle. And if we were to apply sine, cosine, and tangent to the unit circle, that might change the way that we represent, right? So what would we say for tangent of theta if we're looking at the unit circle? Right, so what would we call tangent? Perfect, we would say y over x, right? And if we were to say cosine, that one would be the x value. And if we were to look at sine, that would be the y value, okay? Now, one thing I do want to say really, really great job on is I've seen quite a few of you showing all the calculations for how you get the y over x value. And it is something I promise you, if you're not sure where these values come from, the more you do it, even if it feels really slow and hard in the beginning, the more you do it, the easier that connection will become, all right? And so last but not least, I put a copy of the unit circle here, right? A tiny, tiny unit circle. And one thing that I would really recommend for looking at preparing for the exam is I sort of think about just that first quadrant, right? I've read a lot of different strategies that folks have been talking about on the discussions, but if you know your first quadrant, right, you know all of the angles there, right, angles and radians, and you know all the coordinates right there, that's a really, really good place to be, okay? This is something that when I was taking, even when I took Calc 1 and Calc 2 and Calc 3, literally on the front of every exam before I got started, I would draw out the first quadrant, I would write out all the coordinates, and I would write out all of the angles. It probably took me about 2 minutes to write all of that out. But then when I got to the exam and I could sort of focus on the calculus or whatever content it was, and then if I needed the values, they were already there on the front of my test. Okay. And so that's something that I would really encourage you to work towards, is being able to recreate at least the first quadrant of the unit circle in about like 2 to 3 minutes. Okay. I've had students in the past and who pretty much can do this in about 5 minutes. I think that was like the longest that it was taking people because they had practiced so much on it. And those students who were able to do this, when they got to their future classes, were definitely like, oh, I felt like I knew my values so much better than everyone else. And I feel like it really paid off. And so, you know, I know that's still a story coming from me and not from an actual former student, but I will say that that has been a point where, like, if you can master these values and then think about how to use them, it will definitely make your life easier. Okay. All right, but let's take a look at the what's new. Ooh, I don't know why that's all blurry. All right, what's new? And so one of the things that we're going to start to do is in the what's new column, I like to ask questions, right? And so one of the reasons I like to ask questions is because at the end of the day, we still have to come back and think about, okay, do I know the answer to that question? And so I know sometimes, especially in these 3-hour lectures, it can be like, I don't know what's important anymore. I'm so zoned out. But one thing you can do is you can come back to these questions and say, can I answer them? Do I know how the graph of sine looks? Do I know what the graph of cosine looks like? What do all these words mean? Domain, range, amplitude, period, wavelength. Do I know what those mean? All right. And what are graph transformations? And so for some of us, this might be a way to think about, like, okay, I'm going to read the questions before the lecture. That way I kind of know what to listen for. And for other people, it might be like, okay, at the end of lecture, when I'm sort of studying and really just going back into the content and making sure I understand it, not only do I know how to do the problems, but can I answer these questions? Okay. All right, so let's go ahead and take a look at this together. All right, so we're going to take a look at this graph of sine, and we're going to talk about some important features of this graph. In particular, we're going to look at domain and range and even, odd, neither, and something called the period. Okay. So if you go on Desmos, right? So earlier I had dropped the link for Desmos into the chat. And I think a few of us have maybe entered the classroom since then, so I will re-enter that in there. But in Desmos, all right, if you can go ahead and try and recreate this graph, okay? So in your graph, go ahead and type in sine x, see what you get. And once everyone has done that, if you could go ahead and give me a quick thumbs up in the as a reaction, just so I can kind of see how many graphs we have and how many we're waiting for. Excellent, excellent, excellent. We're still waiting for, I think, about 3 or 4 of us. Perfect, maybe about 2 more people. All right. So we've got this graph here, all right? Now, one of the neat things about Desmos is you can sort of like just click on the graph and then move the graph around. Like literally, if you just click your mouse somewhere and you sort of move the graph side to side, you can see different parts of the graph, okay? So on Monday, we talked about domain and range a little bit. Can someone remind me what domain refers to in general? Exactly, right? So we're looking at the set of X values, right? And so one of the things that we might notice is even though I sort of just did a small screenshot of the graph here, when you move your graph to side, does the graph ever end? All right, we've got one no. Anybody else find an end to the graph, or are we all in agreement with a no? And again, you can do a quick thumbs up if you're like, yes, I agree. Cool. Yeah. When we sort of drag that side to side, that graph does not ever end, right? And so for those of us who were with me for Math 116, we might remember that we wrote that as going from negative, oops, okay, now that worked. From negative infinity all the way to positive infinity is one way of writing that. Or another way that we wrote that was this R with a double line, and all that refers to is all real numbers. Okay. All right, so we've talked about domain, and we could see that just by sort of looking all the way to the right, or maybe looking all the way to the left on our graph and seeing that it never ends, okay? But another way to think about that is that X really represents an angle here, all right? And so if we think about the angles on a unit circle, well, we can keep going around that unit circle as many times as we want, right? Nobody says you have to stop after one time around the unit circle. And so because we can keep going around that unit circle forever and ever, that's another way to think about that domain being all real numbers. Okay. Well, if the domain is a set of X values, what do we have for the range? I agree with that, but let's talk about like a definition first, right? What do we have for the definition of range? Yeah, it's the set of the Y values, right? I really love the attention to notation that I'm seeing in the chat. So we start at -1, we include that, and we go all the way to +1, and we include that. And that's why we use the brackets, right? So if we use a bracket, that means we're including that point. But if we had parentheses, that would mean that we're not including those endpoints. Okay. So we have our range as all the numbers, like what are the possible values we can get for sine? And one of the things I want to remind us of is on our unit circle, all right, we had a radius of 1. All right, a unit circle has a radius of 1. I'm going to change that to has. It's not past tense. It always has a radius of 1. And so that sort of makes sense because we think about what can the Y values on the unit circle be? Well, they can't be any bigger or smaller than -1 and 1. Okay. But if we look at the graph, we could also see that the highest point occurs at a positive 1. So that would be like this 1. But the lowest point is at -1. That's why we have the -1 at that beginning. Okay. All right, let's talk a little bit about even, odd, or neither. So I know that was one of the lessons that I asked you to sort of watch a video for instead of doing a synchronous lecture. I'm wondering if anyone can tell me, based on the picture here, do you think sine is even, odd, or neither? And in particular, why did you say that? Okay, so one of the things that maybe we recall from previous lecture is that if we have sine of theta or of x, right, negative x, that's the same as negative sine of x. And that is indeed correct, that it makes that an odd function, okay? But another thing that makes this an odd function, if we look at a picture, which is sometimes more helpful for some of us, right, is that if we look at the, let's see, what color do we want to use? If we look at the origin, okay, one side sort of goes up, but then the other side goes down, all right? And when that happens, what we have is something called symmetry about the origin. Symmetry about the origin. In other words, if I plug in, let's say we pick a value, right? Let's say sine of negative pi over 2. From our graph, can someone tell me what sine of negative pi over 2 is? Let's make sure we read that question carefully. Sine of negative pi over 2. Okay. Yeah, so sine of negative pi over 2, since this is a graph of sine, I'm going to go to negative pi over 2. And I'm going to find the y value there. That's -1. All right, so what we're looking at is sort of a different representation of sine. Okay, well, separately, can someone else tell me what negative sine of pi over 2 is? Nice, nice. And I really like the way that you put those parentheses in there, Matt. So when we look at our graph, sine of pi over 2 is 1, but then because we have the negative sign in the front, we get -1, right? And when we're talking about this odd identity, that's what we're really saying. We're saying no matter what values we pick for x, if we take sine of a negative value, it's going to be the same as negative sine of the positive value. Okay. So I just wanted to make sure that that was clear. I know that folks have turned in work on the quizzes that look like we have the right answer, which is fair. And I want to make sure we do understand that. So it's not just like a I think if you try and brute force memorize your way through this course, it's going to be a very, very long rest of the semester. Okay. And so really trying to make sure we understand things so we can use them in a different context is going to be really important. All right. The last vocab word I want to talk about right now before we go into our breakout rooms is something called the period. Okay. And so the period means, oops, how long is one wave? That's really the question we're asking ourselves. How long is one wave? Okay. So if I were to, on my graph, trace one wave, all right, I'm going to pick a starting point and I'm going to ask you folks to tell me when I should stop. All right, so I'm going to start tracing and you tell me when I should stop. Okay. So I'm going to start at the origin. All right, so get ready. Tell me when I should stop tracing.
Stop.
Okay, so I think I heard a stop at like this. This is one wave. We agree? Do we disagree? Ooh, we get a disagree. Okay. Dallas, where do you think I should stop? Did I stop too soon? Did I stop too late? Too soon. Okay. I would say that what we've highlighted so far, and let me go over it in the little red laser, this part, right? That would be part of a wave. But in order to get the full experience, right, we want to have all the good times and sometimes we need the not so good times to sort of balance things out. Okay. And so while I would hope that we all just have really wonderful semesters, I want to make sure that we acknowledge that sometimes a natural part of the semester is the good times and the not so good times. Okay. And so I'm going to go back in that yellow and keep going until I get back there. All right. And so one thing I really like is that no one said stop when I got to just like the top of the bump. Okay. Because we're going to go, we have to get all of these positive Y values on the graph. And we did technically get back to like where we started. But what we also need to consider is sort of the negative Y values as well. In other words, all of these values, -1 to 1, we have to see them in a wave. All right. And so when we do that by starting, we get the high points, the low points, and everything in between. All right. But let me erase this for a moment. All right. I'm going to choose a different color. And let's play the same game. I'm going to ask you to tell me when I should stop drawing the wave. Okay. I'm going to start over here this time. All right. And so you folks tell me when to stop.
Stop.
Ah, nice. Perfect. All right. So without that little extra bit, I know that, clearly there's a little bit of lag between my brain and hearing things, but yes, this is exactly one wave. We start here, we go all the way to sort of this low point, but we manage to finish off on a high point, which if you're going to have waves in your semester, that's how I hope it goes, right? I would never want us to sort of end like maybe like down here, right? I wouldn't want us to end off on a not great note, right? So we start here, we get all of these values, but then we also get way back up to where we started. All right, cool. So Now the question is, how long is that wave? And here's how we measure how long it is. We go from where we started. So in this case, I started here, which is negative 3 pi over 2. And I stopped here, which is pi over 2. Can someone tell me how far it is between those 2 points? In other words, what is the horizontal distance that we traveled? Okay, I would agree that it's 2 pi, but I'm wondering if you can unpack that a little bit more for the class. Like, how did we get 2 pi? Great, great. We look at how far we traveled, okay? So let's say that we started at negative 3 pi over 2, and we stopped at pi over 2. Whoops, let's write this differently. So pi over 2 minus negative 3 pi over 2. It's another way that I can write that. I'm just working with arithmetic. Exactly. I could say the negative negative makes that a plus. So pi over 2 plus 3 pi over 2. Can I add these fractions, or do I need to do some work with them before I add them? I can add them, yeah, because we have a common denominator here. So pi plus 3 pi on the top, that gives us 4 pi over 2, and we can reduce that to get 2 pi, okay? And so all that means is that this length right here is 2 pi. Oops. All right. I see a great question that is, can we technically use this word wave? And yeah, we do actually use the word wave when we describe things. And so we will talk about more vocabulary around that. So if you go back up to the top and we talk about things like amplitude, period, and wavelength, we can see that wavelength is actually a technical term. And so it's okay that we use the word wave to describe what's happening here, okay? All right, so let me make sure I write this down here, that the period is 2 pi, because that's how long it takes us to get one full wave. Whether we do the green one that we did right here, or if we went back into the yellow one, which was from here to here, all right, that one actually probably was easier to calculate because we have 2 pi minus 0, which is 2 pi, okay? Now, as much as we might look at all these waves and be intimidated, one of the cool things about sine and cosine is the waves are very predictable. In other words, in one graph of just whatever we're graphing, the period will always be the same. Like how long the waves are will always be the same, okay? All right, so I'm gonna pause the recording here. Great. All right, so in example 1, we have f of x equals 3 sine of 2x. of those numbers, right, we want to think about, do we have a C? Do we have a B? Do we have an A? Do we have a D? Let's choose a different color. All right, so of those 4 types of graph transformations that you looked at in the group work earlier, let's talk about which ones we see here. So in f of x equals 3 sine of 2x, what graph transformations do we have? I would say I agree with part of what you have. There you go. The part I agree with is we have a B value, right? And in particular, which number is our B value? Exactly. This is our B. So we'll call it the same color and oops. And this B actually tells us how many more waves we're going to see. Okay. So now we're going to see 2 waves where there was 1. All right, we're going to see 2 waves where there was 1. And the other letter I agree with is A. All right, we do have an A value. What does this A value do to our waves? What pattern did we notice in the exploration about what that does? Yeah, I think the vertical part I'll take. Can we use a different word maybe instead of growth though? Yeah, like a vertical stretch. Okay, vertical stretch by 3. All right. So when you're doing the work on a quiz or an exam, I think this is a really nice way to sort of start off so that you're sort of setting yourself up to be, to know what you want to be graphing. Okay. And so in this case, we notice that there are 2 graph transformations. And so on our little grid that is provided, we have 3 spots. All right. We always start with the parent function. What does the graph look like before we do anything to it? And then we think about each transformation and what it does sort of step by step, okay? And so in this case, our parent function is sine of x. And so we can write f of x equals sine x in our equation. And we're going to go ahead and graph this accurately using the grid, okay? I draw the first point at the origin. When I go to pi over 2, what is the y value on the sine graph? You can look back at the examples we had earlier, but what is that y value when we get to pi over 2? Yep, and so I'm going to draw a point at 1. All right, when I get to pi, what is the y value there? 0, good. What about at 3 pi over 2? -1, good. And what about at 2 pi? Yeah, we get back to 0, right? Perfect. All right, what about on the other side though? If I get to -pi/2, what should I? Good, I get to -1, and then if I go to pi, 0, perfect. What about when we get to -3pi/2? Good, and at -2 pi? Perfect. All right, so when you are graphing these, please do not just do this and draw a wave, okay? I am showing you, I'm modeling for you what I hope that we are doing. That's why we have the grids provided, because I know that it's a pain to sort of sketch those out, but I do want us to graph those, plot those points. Every time we plot those points, we are training ourselves to know those unit circle values better and better, okay? All right, so we have a B and we have an A, and we know from our little acronym that we are going to start with the letter B. Okay, so the first transformation we're going to apply is 2 waves where there was 1. Okay, and that's so important that actually when I describe it in the graph transformation, I want to say there are 2 waves where there was 1. Okay, and the equation that I'm going to draw right is f of x equals sine of 2x. So just the part with the 2x, okay? Now, one of the most important things about sketching these is something called the center point, okay? And those of you who were with me in Math 116 know that that center point was like really, really important to our graph, okay? So let's go ahead and denote this, our center point, okay? And if I were to trace from the center point 1 wave, I could go up and then down and then back up, right? That would be 1 wave. What is the period of this function right now? 2 pi. Great. Now, look at what we want to do next. We now want there to be 2 waves in the place of 1 wave. So that means that I'm going to have to go up and down and then up and then up and down and back up twice before I get to the same point. All right. How many boxes between the center point and the top point? 2. Okay. So if I want the waves to be twice as close together, should I have more boxes between the center and the top, or should I have less boxes? Yeah, we're going to have less because we're making 2 waves where there was 1, right? We're cramming more waves into that same space. And so the first thing I want us to draw on our next graph is the center point. But now, instead of going 2 boxes over, we're only going to go 1 box over. Okay. All right. After I go up to 1, what should the next y value be? Good. 0. And then? 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. -1, and then 0. Great. So we've got one wave that happens faster than the wave that we saw in the original. Okay. This might actually be, if you really liked the, like, what does the graph sound like from Monday? This could actually be a really fun way to imagine, like, okay, well, what happens? The waves are moving faster, so it's going to sound different than if it's more spread out. Okay. Now, I do want us to draw in all the waves. All right. So we've got our center point here, but we want to continue that pattern. So we're going to go up to 0, -1, 0. That'll be another wave. And then we can do the same thing in the opposite direction, -1, 0, 1, 0, -1, 0, 1, 0. And we get our wave. Okay. We can see here that this, oh, let's choose a different color. This is 2 pi. We hope that down here, the period is going to be only 1 pi. And in fact, we can see that this was 2 pi. Now it's only 1 pi because we want 2 waves where there was 1. Okay. Another way that you can think about this is, instead of saying 2 waves where there was 1, you can say that the x distance between points is half of what it was, right? Instead of the x distance being 2, now that x distance is just 1. All right, the last transformation we have is that a value, or the 3 in the front. And so we're going to have f of x equals 3 sine of 2x. Now we have our whole equation, but we get a vertical stretch, whoops, of 3. Now, what does that mean? That means that we're going to multiply y values by 3. Okay. So let's, oops, I forgot to connect it over here. So let's use this graph, and we're literally going to take every y value on the graph and we're going to multiply it by 3. All right. So start with the center point. What is the y value of the center point? 0. Okay, so 3 times 0 gives us 0. Perfect. So the center point stays where it is. Now, it won't always stay where it started, so that's why we need to keep track of it. Okay. All right. The next y value is 1. So 1 times 3 gives us 3. Perfect. So 1, 2, 3. All right. What about the next point? Where is that going to have a y value? 0. Good. All right. What about the next one? -3. Good. So 1, 2, 3. And then we get back up to 0. Now I'm going to pause right here so that we can sketch in the wave. All right. But now we can see that it's still like the same width as the wave above, right? That period is still the same. But what's different is now we've stretched it to make it taller. All right. And so one of the words that we saw earlier was something called amplitude. All right. So I do want to write that down, that this is something called the amplitude. Okay. Now the amplitude, though, is just from your center point to the highest point. Oh, that's not showing up yet. There we go. Okay. From the center point to the highest point, how many units is that? That's all that's asking. Okay. So what's interesting is it's not from the tip top to the bottom, right? It's only from the center to the top, right? The center to the top. All right, let's sketch the rest of this. Once you have one wave, you literally just keep doing that same pattern, because sine, and we'll find out cosine, is very reliable. Reliable in the sense that the same pattern will repeat itself over and over. So let's get this all on one screen here. And before we move, oops, and the question too, and before we move on, are there any questions about example 1? All right. So let's go ahead and take a look at number 2. All right, those of you who were with me in Math 116 know, hopefully, that this is one of the ones that I'm going to make a really big deal about. And I'm gonna make a really big deal about this because it's the #1 place where mistakes happen, and I don't want that for us, right? I don't feel like I do my job if I only show you like the regular cases, but never the cases where mistakes tend to happen, right? That's like setting you up to like only know half of it, but then get wrong those tricky questions. And I don't feel like that's responsible. All right, so someone who was with me in Math 116, what am I going to ask you to write before you even do anything else? Factor the inside. Yes, thank you. So let's maybe write this here, factor. And if you don't factor it, but you magically get the right answer, I'm going to be like, wow, that kind of looks like you just copied it from Desmos and you don't understand why things are happening, right? So we don't want to sort of go down that path where you're like not documenting your work. And as a skeptical reader, I want to make sure that I can see clearly that you understand the thought process, okay? So we factor out. We're going to have a 2. And what do we have inside the parentheses? Great. X plus pi over 2. Okay. So please make sure that you see that. All right. And then we have our good old phrase, see bad. All right. So what letters do we see here now that we factor? Well, it should be somewhere in notes. Maybe if you scroll around, you could find that. Anybody find it yet? Like where C, B, A, D fall in the equation? So like, how do we know what letters what? I would disagree with you. Has anyone found where CBAD is in the notes? That might be helpful for us to establish first. Great, I agree with all of these numbers, but can we say where in the notes we found these? Yeah, like towards the end, right? In fact, it's underneath the cosine one. Yeah, but it should be down there. Okay, so if you don't remember what that is, you can look back down there to see that. All right, so we've got a B value and we've got an C value, but the way this ordering works, we have to start with the C value, okay? All right, so we're going to start off with our parent function. And yes, I want you to write this again. And yes, I want you to draw it again, okay? And if you're feeling sorry for yourself that I'm asking you to do all of this and you would really just wish that you didn't have to draw this, I draw this every single year, every time I teach this course. So guaranteed, I've been drawing these more than I'm asking you to draw, okay? All right, so we've got our graph of our parent function. The first transformation to happen here is going to be this pi over 2. All right, now based on your transformations from earlier, the explorations, what does that pi over 2 do? Great. Shifts it horizontally, be more precise. Just saw f of x equals sine of x plus pi over 2. It would go exactly, it would move to the left, pi over 2. Perfect. Okay, now I'm moving something to the left. Is that going to change my center point? Yeah, every single point is going to move. All right, including that center point. Now, here's a strategy that some students have used in the past to help themselves keep track of things, which is they don't just color the center point, but they color some other points as well. So they can see like, okay, together, those 3 points, I can see where all 3 points move to, okay? Now, if we are moving to the left pi over 2, how many boxes is that in the x direction on this grid? Great. So pi over 2 to the left is 2 boxes to the left. All right. So first thing I'm going to do, I'm going to take my center point because that is my primary thing, and I'm going to move that to the left pi over 2, and I'm going to get to here. Great. I move the green point over 2 to the left, and I go here, and every point moves 2 to the left. And if you know your pattern, it becomes a lot faster, like I just kind of did, to follow that pattern to make those points. All right. In case you want to try this strategy, the green point moved here, the yellow point moved here. And so we can see that everything sort of slid to the left, 2 boxes or pi over 2. Okay. All right, our next letter, we only had one more, which was 2. What does that 2 do? In other words, what does a b value of 2 do? Great. And which one is it in this case? Are we stretching or are we compressing? All right, I agree. So we have a horizontal compression. And that means that the x values will be closer together, right? Very similar to what we saw in the previous problem, right? Now, here's the deal. The first point you must draw down here. No arguments. The first point has to be your center point. Okay. The first point you draw here must be your center point. Because here's the deal. You were squeezing around the center's point, like you're squeezing things into the center point. That means this green dot is not 2 boxes away now, but it's only 1 box away. And the yellow point was 4 boxes away. So how many boxes away is it now? It's only 2, good. Oops. And then we can follow our pattern to keep drawing those. And we can see again that this green point is half as close. The yellow point is half as close, right? So we can see actually every single step along the way to get to our graph, okay? Any questions about example 2? All right, let's take a look at example 3. All right, so we have our CBAD. Let's identify what we have here. All right, which graph transformations do we have here? Do we have what letters? Yeah, I would agree. We have C, we have A, we have D. What is our C value here? Yeah, the pi is going to be the C value. What is our A value? Perfect. And what is our D value? Great. All right. So that means this time I've given us 4 grids, right? 4 grids because we're going to draw the parent function and then we're going to do each graph transformation in order. Okay. So we'll get our f of x equals sine x. That's our parent function. That's where we're going to start. We're going to go over to our grid. Do I start at the origin or do I start at a different point? Where is that center point for sine? Folks, where is that center point for sine of just the parent function? Yes, thank you. It is at 0, okay? I'm asking this because very quickly, in about 5 to 7 minutes, the center point is going to be different for a different function, okay? So we follow our pattern all the way up and all the way down. It's odd, so we go down first in the left direction and then up. And let's get that center point nice and highlighted so we don't lose track of it. Okay. All right. So we have a C value. So this negative pi here, what does that mean happens to the graph? What does that negative pi do to the graph? It does shift to the right pi. Perfect. All right. And now we have start with that center point. Okay. So we're going to move that center point to the right pi. Can someone tell me how many boxes that's going to be equivalent to here? Yeah, by 4 boxes. Okay. So let's move that center point 4 boxes. We get to here. Great. We can move the next point over 4 boxes as well. And then the next one. And then I think we have enough to fill in the rest of our pattern. Don't forget to dot in that center point so you can keep track of it, okay? All right, what comes next? We're gonna do that 2. We're gonna take care of the 2. And what does that do to our graph? What does that 2 do to the graph? Yeah, it is a vertical stretch of 2. And what does that mean in terms of my graph? Like when I'm gonna draw my graph, what should I be thinking that 2 does? Great. I love the use of that vocabulary too. Amplitude is 2. All right. Great. Now, what does that mean we do to our graph? Like, how do we generate the new graph? Yeah, we're gonna times 2. Now let's be specific. What are we timesing by 2? Each y point. Perfect. All right. So question for you folks. Does the center point stay the same or does it change? Yeah, that center point is going to stay the same because 2 times 0 is still 0. Right? But this point, it's not going to be at 1 anymore. It's going to be 1 times 2, which is 2. Right? Then I just keep following the pattern. We sketch this out. All right. And we color in our center point just so we can keep track of it. All right, we've got one last transformation, that -1. As I'm writing that function down, can someone tell me, whoops, what that -1 does? Perfect. And in fact, we call that a vertical shift. And we move 1 unit down. Okay. All right. Again, let's start with our center point. So comparing this center point to the one on the previous grid, does the center point change? Yeah, it does, right? And so good thing I know where it is. I'm going to move that down by 1 value. Then I'm going to move everything else down by 1 value. And then we connect them. Whoops. We draw back in that center point so we know where it went. And if I zoom in, hopefully that's not too small on the screen for you. Look at where our 1 center point goes, right? From that center point, you can show me that you know every single transformation that's happening. That's pretty cool. Okay. All right, so that was example 3 over here. Do you want to talk about the graph of cosine, right? Before we leave here today. So I do want to talk about that graph of cosine, all right? So If you'd like, you can go back to Desmos, graph cosine, and so you can see that your own picture, but let's go through the same for characteristics here, all right? So what do we think is the domain for cosine? And more importantly, why? Perfect, right? If we use Desmos, we use that technology, we can see it goes sideways forever and ever. So we have the same domain as we did for sine, okay? Now looking at the graph, what is the lowest y values that you see? Great. Bracket, -1. What's the highest y value we see? 1, perfect. 1, bracket, right? Now, is cosine even, odd, or neither? Wonderful. So maybe we remember cosine of -x equals cosine of x. But what does that actually mean? Well, on a graph, it means that if you fold right over the y-axis, that both sides look the same. Okay, so if you're a more visual person, we can see now if we fold over that line, the right half of the graph looks like the left half. In fact, they match perfectly. Okay. All right, what about the period? What is the period of cosine? 2 pi. All right, let's check that out. If I start here, I am only halfway done with the wave. And I have to get all the way back up here to be fully done with one wave. And that is at 2 pi. So very nice. Period is 2 pi. Okay. Now here is where I was referring to those letters that we had. All right. Now it turns out we don't just go from left to right, but we start with the C value, because if we were to plug in an X, the first thing we would do is minus C. The next thing we would do is multiply by B. So that has to be here. Next thing we do is we multiply by A after we cosine. So A comes next. And then the last thing that we do is the D. All right. So some of you might have asked earlier, like, why do we use some of these letters? And it's not true for all of them, but when we have A, we can think about A for amplitude when we're talking about a sine or cosine wave. Okay. B is a horizontal stretch or compression. C, we tend to call something a phase shift. Okay. Now, I know someone was asking earlier, like, is wave a really formal thing? It is. And instead of saying like a horizontal shift, we actually call this a phase shift. Okay, a phase shift. You'll only hear that when we talk about like sine and cosine. All right. And this D, last but not least, is a vertical shift. Right? All right, so I want to do one more example with you folks, and that is actually not example 4, right? I think we'll leave that to you for some extra practice if you'd like, but I would love to take a look at number 5 together, okay? No, D is not a phase shift. Phase shift specifically refers to that horizontal motion. Okay, so specifically to the horizontal. All right, so with number 5, what is the thing I'm going to ask you to do before you write anything else down on this paper? We're going to factor, okay? So if nothing else, I aim for my lessons to be consistent in terms of the things that I'm asking you to do or to remember. And so this is one of them. I don't know why the sharing is not working right now. There we go. Okay. All right. So when we factor, we've got cosine. We factor out that 1/2. What comes inside the parentheses? Nice. X minus 2 pi and then plus 1. Okay. Now I do want to do this example together because I think it's tricky when we're factoring out a fraction. But one of the easiest ways we can do is sort of factor this out and then think, okay, 1/2 times what is going to give us pi? And I think we can all answer that, right? 1/2 of 2 pi is pi. And so that's why we have a 2 pi after we factor, right? Looks like we've got a C value. Looks like we've got a B value. And looks like we've got a D value. Okay, so we're going to do those in that nice rainbow order. We're going to start with the pink. We're going to move to the orange and we'll finish off with the blue. Okay, so we're going to begin by writing out our equation, cosine X. And here's where I need you to help me plot the points. Do I start at the origin? Yes or no? No, okay. Where do I start? 0, 1. All right. The reason why we need to be so thoughtful about this is because ultimately sine and cosine, they both look like a bunch of waves that go on forever and ever. But they are different, and we need to acknowledge that difference in our graph, okay? This, my friends, is also our center point, right? So we're gonna make sure we highlight that so we can keep track of it. All right, where do I go from this blue point? Let's say we're going in this direction. What is the next point that I should plot? Pi over 2, 0, good. Does it keep getting worse or does it get better at this point? It gets worse, right? Again, that's not my hope for your semester at all. But once we hit rock bottom here, right, the very lowest point on our graph, one might even call that a minimum, then we can start to go back up through 0 and at 1. All right, so we have the left or the right half of our graph here. All right, now, what do we do on the left-hand side of this graph? Same but reflected, right? Cosine is even. Let's take advantage of that. it's going to be mirroring exactly what we saw on the other side. All right. So we have our cosine graph. All right, next thing that happens, x minus pi over 2, or minus 2 pi. What does that mean? What does that negative 2 pi mean? Perfect. Phase shift to the right by 2 pi. Great. How many boxes is that? That is going to be 8 boxes. And I believe by all of them, you mean the ones on like one side of the graph, right? So now we can go ahead and take this center point and it's going to move right to the very edge of that graph at 2 pi. All right. Now, all of these points are now off of our grid. Oh, it's still freezing. Hold on. Oh, there we go. Okay. All of these points are like off of our grid now, but we can think about what the other points look like on this side. Okay. So we'll fill those in. We'll go down to 0, rock bottom, and then back through 0 and at 1. And we want to be thorough, and we'll keep drawing the second period as well, the second wave. All right. All right, what do we have next? We have this 1/2. And as I'm writing it down there, let's throw into the chat what that 1/2 means. Great. That is going to be a horizontal stretch. How far, how much do we stretch? We are going to be doing a horizontal stretch, but I want us to keep in mind what that 1/2 also means, right? And the 1/2 means there is now a half a wave where there was 1, okay? In other words, I see 1 wave here, but now in that same space, I'm only going to see like a half a wave. Okay, so it's going to stretch out sideways. The first point you must draw is your center point. Okay, if you do not start here, and I'm going to feel not bad for anyone fast forwarding through this part of the video later, if you don't start from the center point, your graph could very well be incorrect. Okay. What's the x distance between these points here? How many boxes? It's 2. Okay. So now instead of 2 boxes, we're going to want 4 boxes in between. So that means that we don't get to 0 until we get to pi. And then we have this point down here. Everything is now 4 boxes away from each other. And you can see that we have a really stretched out graph. Okay. All right, last but not least, we had a +1 here. What does that +1 do to the graph? Perfect. We're going to shift that up by 1. Great. We're going to start with that center point. Center point goes up to here, and then, whoops, and then everything else follows. All right. So you'll have a chance to practice a lot of this on quiz 6. All right, you'll have a chance to practice the graphing. Please make sure that you are using this sort of modeling. All right, thinking about things like piece by piece, so that we can make sense of what you have on your paper. Okay. So folks, if you don't have any questions, then we are done here for today.